afternoon again, everybody. This one's on, as I said, advanced weld inspections using phased arrays. And first of all, we're going to talk about, give you an introduction to phased arrays. You've probably already got that. Mention our equipment briefly, very briefly. That's already been done. And I'll start giving you some practical solutions to advanced inspection problems. And there's quite a few advanced inspection problems. Pipe Wizard, which is a pipeline inspection system. Inline inspection using pipe mills, we do that too. Austenitic welds. And a few words of conclusion. So first of all, how do phased arrays work? What's this one? I'm not wanting it. Basically, this is how what an array looks like. These yellowy blocks on the top here. And these are the applied time delays. Your phased array system it's basically a conventional ultrasonic system with multiple channels and built-in time delays. That's the time delays that do the phasing. So the time delays are all important. And here you can see a schematic showing the typical time delays applied to the array down here. And you can see that it focuses accordingly. So essentially, if you put a non-time delay beam across there, you get a flat beam. So it's just the same as conventional transducers. If you put a highly focused beam on there or a highly time delayed, you get a focused beam. And this gives you a large range of focal depth, i.e. focusing, and you can adjust it every pulse. And since you can do about 10,000 pulses a second, this gives you quite a lot of opportunities to alter your pulsing rate and so forth. So that's how you adjust your focusing, and this is how you do your beam steering. And you can see it's very much the same kind of thing. The only difference is that the time delays are not exactly uniform on either side, which is not a great surprise because that's how you get your beam steering. And this gives you a large range of inspection angles or sweeping. It does not give you an infinite range. That is, first of all, physically not possible, and it's also practically not possible as well because you have to calibrate, you have different materials, and you get serious beam distortions at the edge. It also allows you to generate multiple modes with a single probe, shear wave, L wave, creeping wave, and a few other things. There are quite a lot of common probe geometries. 90-odd% of the probes you'll come across will be linear arrays for two obvious reasons. The first is there's an awful lot less elements in there, so they are a lot cheaper to buy, and that particularly applies to the instrumentation. The arrays themselves are generally not as expensive as the instrument. The other thing is that with this kind of array, you can do pretty well everything that you're likely to want in AWS. You can inspect wells, you can look for corrosion, you can look for defects, and all the rest of it. So they can only steer in this direction here, sweep and steer in this plane. And that tends to be enough because once you put it on a scanning jig, you can motorize the scanning jig and you've got a fully automated system. If you want to get very fancy, you can try one of these guys. These are matrix arrays and they get very fancy and they're usually custom built and they cost. So these things come off the shelf, at least they do from us. And the other ones are custom built, so these will take maybe 10, 12 weeks and probably cost you about the same. They're a bit of a pain. And these are special arrays too. All three of these are specials generally, and they take a long time and a long way. The other reason for using a linear array is it's also a lot easier to program. Our instruments are pretty well set up for programming linear arrays. If you want to get into a fancy array, then you need to use something a more exotic way of programming. And the first and probably the most important concept about phased arrays is it's basically ultrasound. You are not changing ultrasonics. And the few tests that we've actually done or witnessed or simply reported which basically show that you get the same results with a phased array as you do with conventional ultrasonics, which is quite encouraging because it means you don't have to change the acceptance pricing procedures, criteria, I should say. Really what phased arrays are is a fancy method of generating and receiving a signal, and they're also great for showing images. And the imaging is really a very important aspect of phased arrays. So what this means in practice, if you get XTB or bubble below the threshold using conventional UT, you should get something pretty similar using phased arrays. And typically you do within a dB or two, which are due to coupling differences, calibration differences, etc., etc., etc. There's lots of reasons why you don't get identical values. You don't even get identical results with conventional phased arrays. How do they actually work? Well, the operator puts the focal depth. We have a setup program, a wizard basically, that takes you through the system. So the operator sets the focal depth if they have one, inspection angles, that's important, and the couplant type of scan, how many, which elements are to be fired. And that's not such a big deal. You can do that quite straightforward. You also need to input details on the array and the wedge. That, in general, is not difficult either, particularly with the portable OmniScan thing, the devices. You hook it in, it's got a chip in the array, it automatically reads the array, and it tells you what type of array you're using. Very nice. You do have to put in details on the wedges, but they're written on the sides of the wedge. So we like to make it easy for the operator. This has been quite a change in the last 15 years. 15 years ago, we didn't get useful like that. Then we have a little computer inside the instrument that's called a phased array calculator, and it calculates what time delays to apply to each of the many elements. And typically, if you're firing 16 elements, it will give you the time delay and all the different elements and all the other parameters that you want to know. You, as an operator, do not have to do very much. Okay, so how far can you scan with your angles if we're doing a sectorial scan? Well, first thing you do is you look at the manufacturer's angle range in the catalogue. In our case, it's based on physics, so when the beam is bumping into the end of the wedge, then that's it. You cannot go any further than that, otherwise you lose half your beam. That's a kind of no-brainer, if you like. But more to the point, you have to calibrate as well. ASME code requires you to do that, and I suspect other codes when they come out will require you to do that too. If you cannot calibrate over the range that you think you should be able to calibrate over, well, that's life. What happens is, at the lower end of the range, you see these beams that look like this. Well, as you go away from the natural wedge angle, the signal amplitudes tend to drop off. Also, as you go further and further up, they drop off further. So you get to the stage where if you're trying to calibrate at an 80% threshold, you're down at 5 or 10%, you're going to have real trouble calibrating. So you kind of cut down your range, and that's the situation. It also depends on a lot of other factors, particularly the material, and I'll stay off that one right now. And of course, we also have come up with some interesting array designs, particularly using sparse elements, and they're a bit of a different headache, and we'll stay off that too, I think. Now, I'm sorry guys, this is supposed to work. This is supposed to be an electronic scan, which means you take your array and you just scan along it like that, and the simulated beam is supposed to run along like that and do a scan. It's a corrosion map, if you like. We're also supposed to be doing some, get one down here too. Sorry, my animations were working the other day. This is how you do welds. You have an array on either side, and the beam goes down there and up there, and it inspects the welds. And as you run along the welds, this way, you electronically scan this way, it scans up and down the well like that. So you just need one axis of motion, which is why they're called linear scans. There's a problem with welds, as you probably gathered, that you need to have good orientation for your defects down here with your bevel incidence angle. And this can be a real headache, because if you're doing an S-scan, you get wonderful coverage all over the place, but you don't necessarily get good angles. So what we did was we came up with some rudimentary rules, should we say, at least for ASME, that allows you to use an S-scan under various conditions. You're supposed to use appropriate angles. The level 3 is supposed to write a procedure that ensures that you use appropriate angles. In fact, what the level 3 is really meant to do is use the scan plan software that allows you to predict what the angles are, and then they can make intelligent decisions about that. Well, I'm sorry, this is another one that was supposed to be animated, and was supposed to have a beam that comes down there, bounces back onto there, and bounces back to the array. And this is specifically designed for vertical defects. We have other techniques like TOF that are very good for vertical defects. This is an alternative, and it's used a lot in the pipeline industry because they're using gas metal arc welds, which are real vertical. And that's primarily, again, for speed. Another possibility is to use time of flight diffraction using phased arrays. Again, this is mostly used in the pipeline world, if they're going to use it, because here you can see, here you are using separate transducers. In the pipeline world, sometimes they don't want to spend the extra money on the transducers, so they use what they've got already, which is the phased array probes. There are some disadvantages in doing that. The frequency tends to be a bit lower, the probes are not that well damped. So basically the resolution is not as good. However, if you're primarily looking for detection of defects and you've got a tandem probe type backup, then you should be okay. But this is a picture of a phased array of a TOF scan, and you can see you get signals off the tip, which is this one here. You get a signal on the bottom, which is this one here. And if you're lucky, you get a phase shift, and you can measure the top and the bottom of the defect, and you can compare them with a lateral wave, which is this green one running across there, and the backboard echo, and you get a wonderful picture that is so useful for you that you can just analyze that for you, despite what John really says. Anyway, back to the subject of phased arrays. This is an S-scan, and it's sweeping through a range of angles, as you can see here. And this is a defect at the bottom, which correlates with what's called T1, which is the top of the full skip scan in our world. And you can see there it is up there, and you can see it correlates to a defect that's at the top. Likewise, this one down here correlates to a defect that's at the bottom, or half skip, and you can see that it correlates with B0. Fine. So you get a nice image of your weld. If you have something in the middle here, well, that's a mid-wall defect. Life is fairly straightforward in this respect, and you can see where it is, what it is, and all the other factors related to it on the whole. Interpreting the data is probably the single hardest thing that you get with phased arrays. It's quite easy to set up the scanner. To calibrate it requires practice. It isn't really impossible. But interpreting the data with more variables in this particular game makes everything else. You can also use phased arrays for sizing, and they're really pretty good at that for a couple of reasons. Here you see a weld bar with a crack in it, and that's the reflection from the corner of the defect, the corner track. And on the top here you can see another rather weak little signal. Now this would be the equivalent of a non-standard scan because you're running probably quite a lot higher than your standard calibration levels, but you can see a point which shows the bottom and you can see a point which shows the top. And this is rather useful information, especially if you want to size it. You can put your cursor on the top, and you can put your cursor on the bottom, and you come up typically with an accuracy of about plus or minus 1 millimeter. So, what do we have in the way of equipment? Well, we have an MX2, which Dave didn't show you the last time, but you can see a couple of pictures of it here. It looks very much the same size and shape as the previous machine, only there's a bigger screen, and it has a touch screen as well. We have something called a focused LT, which tends to be the next level up. It's quite advanced. You can program it with turbo view and do all kinds of tricks. It's not really for beginners. It also gives you flexible access control, remote control, and various other parameters like that, which are more than you really want if you use a portable instrument. We also build a machine called Pipe Wizard. This is for using on pipelines. You can see this is the old one. We came up with a new version down here, which is much downsized and is actually portable as opposed to this one, which is barely movable. And basically, we took all the same technology and repackaged it into a highly reliable solution for onshore and offshore inspections. And we've sold a couple of hundred of these things, so we're actually doing quite well out of this. Based on focused LT with a 64-128, so we can use matrix arrays if we want. We've scanned millions of welds, and we've used it in all kinds of places. We have some pictures of these scans, Siberia, Middle East, whatever. Okay, the biggest problem with it used to be the umbilical cable, because we had an umbilical that ran from here all the way to the, ran from the scanners all the way to that, and every once in a while somebody would run over it and crush it or whatever. And also they had problems with the mini cables inside. One of the things about a pipeline or a phased array system is you have 128 channels there, which means that you have 128 mini coaxial cables. And these mini coaxial cables are just rubbing against each other quite a lot. So we solved that problem by potting the cables, and essentially we have virtually no problems from this umbilical anymore. Another thing we've developed is the cylindrically focused arrays. Now you notice this one here has a sort of focus on it. Well, the way ultrasound works, once the beam goes into the pipe, it inherently defocuses. And the smaller the pipe, the worse the defocusing. And it's not that bad on the bigger pipes that they use for gas main lines, but if anything smaller than that, you know, the little pipes, it becomes an issue. So what we've done is we've built arrays with their cylindrically focused range. And what they did was they focused the inside, they put a flat on it, they design a wedge that's just standard for anything else. So when you're doing any replacements or anything, wedges or anything like that, you just pop on, pop off a smooth-faced wedge, and you don't run into problems. But you can see the effects of it here. These are the width of the defects before focusing, and these are the width of the reference calibration factors, and these are the widths after focusing. And you can see down here it makes a substantial difference. You always get a certain amount of beam spread with ultrasonics, as we're probably be aware of, because we're not looking at lasers. Another thing that's come up is back diffraction sizing. This has been driven by Trans-Canada Pipelines, who came up to us quite a long time ago and said, we need to size defects accurately to within an error of plus or minus half a millimeter. And we said, you're joking. And they said, no. And so we're now working on this technique. And you can see here that we've got a couple of defects here, and we're struggling to get to within plus or minus half a millimeter anyhow on this kind of thing. But we are working on some signal processing techniques that make these kind of results look potentially quite good. The accuracy is much better now. We can also run S-scans and E-scans all at the same time. And the reason for that is quite simple. Because we replace the old focus machine with its relatively slow data transfer rate with the new focus LTs, we can bang data through at a very much higher rate, so we can actually run S-scans, E-scans, and all the strip charts at the same time. Now, if you look back at the codes in this game, which is 1104, ASTME 1961, and the DMB 101, you'll find that all of them require you to do strip charts, because once you get into this game in pipelines, you realize that that's probably the fastest way to go. And that's what they're looking for. Speed, speed, speed. That's the same with the welding. So what we have to do is to come up with these S-scan images as well. So we just produce those kind of images to start with the strip charts. When anything controversial showed up, we pick them up here. So you can see root reflectors, cap reflectors, whatever, are all shaping up. Okay, something else we build is an inline inspection system. This particular one is using a water wedge. We have two types, a water wedge and a stuffer box. And this one uses a unique water wedge concept with holding a different type of probe holder and cylindrical phased array probes. What we do, acrylamide is the name of the rubber at the front, but we have these curved arrays that are more or less matched to the diameter of the pipe. So we have half a dozen arrays cover everything else, because when you go and talk to a pipe mill, you discover that they have 100 different types of tubes, and you'd better have something available for every single one of them. So they give you your specs and off you go. This particular combination here uses a water wedge. You can see a drawing of it down here, mounted on whatever. And it has a suspension system that follows the pipe movement. This is quite convenient, and if anything goes wrong, it lifts the water wedge. You've got scarfing or weld joint or something or other, it lifts it up and bounces it over, and you probably have to rescan some more later on, but that's another story. The main point is that you don't destroy the wedge and you don't destroy the ray. We even have an automatic calibration sequence for this. You can see that we've got a sample up here. It runs over that little notch there, and it calibrates itself. This is a typical example of the printout. I presume the green is good and the red is bad. I never thought to ask that question actually. And you pop out your amplitude, and it gives you the figures down there, and that gives you detailed and recorded values for your calibration. We can do this on round bars, square, well, not so much square bars, we do it on all kinds of different bars, anything above about 65 millimeters, and they use these in the automotive industries and a few other places. Lastly, the other one I'd like to talk about is austenitic weld inspections, which unfortunately keep coming along, and in fact are getting worse, or more frequent I should say. And these are challenging inspections. Radiography does not do very well on austenitics because the grain size varies a lot. What's happened is with austenitics way back in the 50s and 60s, the US nuclear industry used a lot of centrifugally cast stainless steel pipes. And these were made of stainless steel and they grew huge grains. The grains are so big you can see them with your naked eye. You don't even need to measure. And these grains turned out to be absolutely horrible when it came to doing any type of inspection. The nuclear industry didn't want to use radiography, they wanted to use ultrasonics for a variety of reasons, and ultrasonics really fell badly. So what they did was they did some research on this, and they discovered that longitudinal waves were much less affected than shear waves. The shear wave suffered all kinds of problems. Beam steering, splitting, refraction, absorption, you name it. We also came up with dual arrays, so there's a repulsor and a receiver. That cleaned up your noise a bit. The problem is that every single case, every weld, whatever you like it, is basically a special, so you need to work out your own techniques for that particular weld. The good news is that once you've got your WPS worked out, that will then be pretty much a standard microstructure. So you just get a standardized weld, and off you go. You just side your holes or whatever. Here's some of the results they came up with. That's an L wave. That's a shear wave. It looks absolutely terrible, I think. Yeah, that's an L wave at the top. The next one down is a SH wave, SV wave. And this is a horizontally polarized wave. It's not so badly affected. Of course, SV waves, which are the standard shear waves used in ultrasonics, are the most damaged by this technique. And we have a transmit-receive phase array system down here, which is very much the top end of the austenitic weld inspection techniques. So yes, we do have solutions. We have the guidelines, and we can help you with that. But here's an example of what they look like. We can solve today, if you get a standard WPS, this would be the cladding on the inside, or a clad weld, and this would be part of the weld itself. And the grains are larger, so you see more noise, and that's quite expected. Okay, all the welds are different, we know that. This is typically what you end up with. This is a stainless steel weld with a down defect down here, which is a lack of sidewall fusion in this particular case. And you can see it here, and it's here. Again, you see this 3D imaging that you see you get in phased arrays. So, as far as phased arrays are concerned, there's a lot of advanced developments on all kinds of different areas. Pipelines, they're cladding them, which is a bit of a headache. There also have things like seamless pipe and so forth, where you can take advantage of the multiple setups. Pipe mills, they're always a challenge. Austenitic, they're restricted as limited. Oh, okay. There are more developments on the agenda.